Let's talk about Boyles Law and vital capacity and other pulmonary volumes. So Boyles Law is one of the classic gas laws learned about in chemistry, and it relates volume and pressure, and those two are inversely related. So the idea is that as one goes down, the other has to go up, and vice versa. If one goes down, the other goes up. So if pressure goes down, volume goes up. If volume goes up, pressure goes down. And that is expressed in this relationship that you should be comfortable working. It's not complicated. You've probably seen something like that in chemistry, where you had V1C1 equals V2C2, volume and concentration. They're inversely related. So the idea, it's shown on the left, is a volume of gas, and the red dots are gas molecules of whatever, oxygen or carbon dioxide, water vapor, anything that's a gas. And they've just sort of arbitrarily given it some values to keep the numbers easy. Volume is 1 liter, and pressure is 100 millimeters of mercury. And if you reduce the volume, this is a plunger in the little cylinder, and if you depress the plunger on the right, plunger has gone down. You've reduced the volume down to half of what it originally was, so now we're at half a liter, and the pressure doubled. So it went from 100 to 200. So you should be able to plug those numbers in. Here's V2 and P2, and V1 and P1. You should be able to plug those numbers into this equation and show that those two are in fact equal. Crunch the numbers, convince yourself, and you should also be able to solve for any one of those 4 terms if you are given the other 3. So let's say solve for any term, any of those 4 terms, given the other 3. So if you had everything except P2, you should be able to set P2 equal to the other 3. And figure out how you do that. There's no multiplication division. It's, well, you will have to isolate P2 if that was what you're doing. So play around with that. We can do that during office hours if you have trouble with that. But do make a note of being able to do that. The next slide applies Boyles' law of volume and pressure. And 2 figures. The one on the left is breathing in, and the one on the right is breathing out. So let's just work through these together one at a time. So during inhalation or breathing in, you're relating volume to pressure. So think Boyles' law. And the volume is determined by the volume of the lungs, the rib cage, the thoracic volume. So during inspiration, you know that the inspiratory muscles contract and they expand the rib cage. The volume increases. So the chest expands. So volume has increased. So what happens to the pressure? The pressure goes down. Now it's all relative to the atmospheric pressure. And the atmospheric pressure, the ambient pressure in the room or outside, doesn't change. That's pretty constant. And what does change is the pressure in your lungs. So back to inspiration, the chest expands. You know that the pressure then has to go down. and it goes down relative to the atmospheric pressure, which is higher, so the atmosphere literally pushes air into the lungs. That's what we sometimes refer to as suction. Somebody sucks through a straw, they go, we think of suction, but actually it's just air pressure being pushed in through the lips to fill the lower pressure in the lungs. So something to remember is that inspiration requires muscle contraction to expand. Inspiration is active. I've mentioned this before. It requires energy. So what causes the expansion? Well, the diaphragm is the main muscle in respiration. It contracts and it pulls down, increases sort of this vertical distance in the rib cage. That increases, and the chest expands and the ribs come out. So it just leads to increased volume. The other side of the figure, expiration, is just the opposite. The chest volume contracts, so the chest contracts, elastic recoil of the cartilage, the ribs, gravity, etc., causes the rib cage to collapse on itself, and the diaphragm relaxes and moves superiorly, and that reduces the volume in the lungs. So what happens to the pressure? The volume has decreased, so the pressure has increased. So as the chest volume contracts, volume gets smaller, the pressure in the lungs increases relative to the atmosphere, and then the lungs literally push air out, and we exhale. And this is mostly passive. Relies on elastic recoil of the chest wall and the alveoli. So the work of breathing is on the inspiration. This figure is, I like, for a couple of reasons. One, it tells a pretty neat story. And what I encourage students to do in science classes, A&P and 160, is to be comfortable interpreting diagrams and figures. I feel it's sort of part of basic scientific literacy or science literacy. What's the picture and what's the story that it tells? So if you are uncertain, you just need to break it down. Break down the picture and set the timer and spend 5 minutes on it, and you should have it down to where you could explain this to somebody else. So let's just go through this together, because I do want you to be able to interpret rather simple figures like this. So what we have on the bottom, we're breaking it down piece by piece. So we're going to start at the bottom panel, and what does it show? Well, it shows time in seconds for inspiration. So we have a 2-second inspiration, we're inhaling, 1001, 1002, and then we exhale. And then we do it again. We inhale and we exhale. All right, so that's the time frame. What's the vertical axis? Well, it's just the volume of air that's moved in the lungs, and this is the tidal volume. So, I just erased all the numbers. That wasn't helpful. So, you inhale, inspiration 2 seconds, and the volume in the lungs goes up until we're up to about here. I don't know, maybe it's 0.6 liters, whatever. It's pretty close to half a liter. And you exhale, and then the volume goes down. So the volume in the lungs is increasing, decreasing. And that's just what we refer to as tidal breathing. It's sort of like the tide coming in, the tide going out at the ocean. quiet, passive, normal breathing. About 500 mils. Okay, that's the bottom panel. That's pretty straightforward. What does the upper panel show? Well, it's the same time frame. So, it goes all the way up. So we have inspiration on the far left, expiration, inspiration, expiration. Okay, and what does the vertical axis show? Well, it's the number of active inspiratory neurons. So these are nerves going to what? The inspiratory muscles. So what are the inspiratory muscles? Well, you should be able to rattle those off. The diaphragm, the sternocleidomastoids, the scalenes, and the intercostal muscles. The external, if we're inspiring. So these are the number of neurons that are active to those muscles. Well, what does it show? That when you start inspiration, when the diaphragm starts to contract, there are few neurons. There's the number. Whatever it is, it's not on the scale, that are causing those inspiratory muscles to contract. And as inspiration proceeds, there are more and more neurons that are active. These are motor neurons to those skeletal muscles. And when we're fully inspired, maximum number. And this is that sort of tidal breathing. So it basically just shows that the skeletal muscles become more active with inspiration. And then when you expire, when you exhale, those motor neurons go quiet and the skeletal muscle relaxes. We get down to sort of a baseline. And this is passive. Doesn't require muscle contraction. So that's what that's showing. I kind of like the figure. It should make sense. If it doesn't, spend a couple more minutes at it, and if it still doesn't make sense, then I'll get a hold of me during office hours or shoot me an email. Okay, so that's that figure. Let's go to the next slide. And what do we have here? Well, there's two curves, again, on the bottom. Just break it down one piece at a time. This is the volume, and the screen looks like it's a little cut off here. Let's see. Not much. So this is breath volume. I did cut off the 0. But now if we have 0 here, this is not saying that the lungs have 0 volume in them. No, there is air in the lungs. All we're measuring on this breath volume is the increase in volume and the decrease in volume. And for tidal breathing, that's about half a liter, about 500 mils. But there is other volume, of course, in the lungs because they're not fully collapsed ever. So the second part of this figure, again, we're dealing with Boyles Law. So we've got volume and pressure. Volume is shown on the bottom panel, and pressure is shown in the middle. And at the beginning of the respiratory cycle, no change yet in the volume. Airway is open. We haven't started to expand the rib cage. We have not started to expand the volume. The volume is not moving, so pressure is 0. It's the same as the atmospheric pressure. They're equal. Because what we're doing is changing the volume in the lungs relative to the atmospheric pressure. Because the atmospheric pressure doesn't change while we breathe, of course. What does change is your lung pressure. Okay, so as we start to inhale on the bottom, you know that the volume in the lungs is increasing. And as it increases, the pressure goes down. So volume increasing, pressure decreasing in the lungs. And the top panel is representing alveoli. And as we start to inspire, the alveoli and the chest volume, the lung volume increases, and they show little arrows showing that the alveoli stretch and expand. And as they do, the pressure goes down. And we are increasing, air is moving in, and the volume is going up. When we have fully inspired and we're at the maximum volume that we're going to be at, right here, there's our maximum volume, 500 mils. So we've inhaled, and if the airway is open and the rib cage isn't moving, then there's no change in volume, there's no change in pressure. And if the airway is open, the pressure in the lungs is going to be equal to the pressure in the atmosphere. No difference. So you can take a breath, and I'll demonstrate this. You inhale, and if I hold it, my rib cage is staying expanded by the skeletal muscles, but the airway is open, the volume is increased, but if there's no change in the volume, if there's no change in my chest volume, then there's no change in the pressure. So if I go, and if I have an open airway, then the pressure in the lungs is the same as the pressure in the atmosphere. And that's why we're at 0. And then I start to exhale, the lung volume collapses, and the pressure goes up. And here's the increase in the pressure. And that increased pressure then forces the air out. So play around with this diagram until you're comfortable with it, until it makes sense, and then move on. But you may have to enlarge it, but take a look at the pressure changes. Now these are alveolar pressures, again, relative to the atmosphere. So it's a little hard to read, but that's the pressure in the alveoli. At this point in the respiratory cycle, it's 0. Airway's open, there's no change in the volume. And then as the volume starts to increase, the pressure goes down. This is now -1. The volume is fully, rather full inspiration, half a liter, airways open, 0. And then as we exhale, the volume in the lungs gets smaller and the pressure goes up. So play around with that until you've got it. Ask questions if you have trouble with it. The next figure is looking at a spirometer to measure lung volumes. So this is a spirometer machine, and it measures pulmonary volumes. There are different types of spirometers. We have one in the lab. It's a little bit simpler than this, but the idea is the same. Patient breathes into and out of a hose, and then that goes to a machine that registers the volume of air moved. And on this device, the drum goes round and round, and as it spins, the little needle, the little pen, goes up and down, tracing the volume. And then you get a tracing like this, and it just shows, again, the tidal volume. Increase, decrease, etc. That's pretty straightforward. The next figure shows the other pulmonary volumes that can be measured using a spirometer. So break it down, and this is our tidal volume, Should be pretty comfortable with that. It just goes up and down, and that's about 500 mils. So it looks like it's going from about 2,500 to about 3,000. So there's 500 mils. And you know that you can inhale more, you can inspire more. So if you're doing a quiet tidal breathing, you can inhale more. Maximal inhalation, that takes us up to the top. Maximum inhalation, and you know that you can then blow everything out of the lungs as much as you possibly can. And that total volume is the vital capacity, VC. And that just sort of maps over to the third panel. So there's that vital capacity again. Okay, then you just break down the other volumes. Here is our inspiratory reserve. So this is our tidal volume. TV, I'm running into this next figure, so don't worry about this one. And this is our tidal volume, about 500 mils. And then the extra volume that you can inhale is your inspiratory reserve, which we'll just abbreviate IRV. Likewise, the expiratory reserve is this volume. And if you add all three of those together, you should wind up with vital capacity. So we could express vital capacity as VC, vital capacity, it just equals the sum of those other three. Doesn't matter what order you add them. Tidal volume plus IRV plus ERV. You could add them in any order you want. The sum will still be the same. And likewise, with the other example, you should be able to solve for any one of these terms if you're given the other three. Solve for any term if given the other three. And here there is no multiplication or division. So all you're going to be doing is adding and subtracting. So practice rearranging that. So if you needed to figure out what the inspiratory reserve volume was, IRV equals, you fill it out. So you're after this inspiratory reserve volume. I'm just looking at it, it seems like, well, take vital capacity and subtract the other two, and you're left with the brown IRV in the figure. Okay? The residual volume in this figure is that volume in the lungs that you cannot exhale. You cannot fully collapse the lungs unless you get squished flat, run over by a steamroller or something, and that just squeezes all the air out of the lung. Otherwise, there's always a residual volume. If you knew that, then you could figure out what the total volume was. But since we can't measure the residual volume directly, it's estimated. So that's it for this section. Please practice this business of calculating lung volumes. Make up some story problems if you want to. It's pretty straightforward. Okay, that's all for now. We'll see you shortly.